In the next part of the lecture, what we're going to investigate is actually the relation between x star of s and x of s, to try to understand better, again, what this x star of s is, and most importantly, because investigating this relation, we'll actually obtain a theorem, the Shannon theorem, that gives us an indication on how to choose the sampling time. Okay? So let's write x star of t. So we have found that x star of t is equal to x of t times the train of impulses. Okay? Now, these can be rewritten in the following way. What we have changed is just that k, instead of going from 0 to infinity, goes from minus infinity to infinity. Okay? The reason why we can extend this train of impulses also to minus infinity is because x of t is equal to 0 for negative times. So whatever happens on the left-hand side, so when k is negative, will anyway be 0 once you multiply for x of t. So we can extend the sum to minus infinity. Why we want to do this? We want to do this because now the training of impulses is actually a periodic signal, because it's a train of impulses of period t that goes both forward and backward in time. So now this train of impulses is periodic, and we indicate the product of these two signals as x of t times delta capital T E of t. So the train of impulses is periodic, okay? And so we can represent this function with a Fourier series. Now, the Fourier series, in particular, will have a frequency, omega of s, that is equal to 2 pi over capital T, okay? Now, what we want to compute are the coefficients of this Fourier series. By definition, if you look up the complex Fourier series, the coefficients are computed in this way, okay? So this is the formula for the coefficient. Now, this integral is actually very easy to compute, and the result of this integral, of this expression, is actually just 1 over t. So let's show this at the board to make you understand why that's the case, if that's not clear. So if we look at the function, we see that we have a train of impulses that multiplies e power minus j n omega s of t. Okay? So the question is, what happens when you compute the integral of a function multiplied for an impulse? So let's look here at this example, in which we have a function, an integral that goes from minus infinity to infinity, and this function multiplies an impulse that is shifted to t0. So this function, this direct impulse, is 0 for all values of t that is different from t0, and then is infinity at the value of t0. So it means that when we multiply this for f of t, it doesn't matter what happened far away from t0. So we can remove all these, all the base of the integral apart for around t0. So this is just on the left of t0, and this is just on the right of t0. So this is t0 minus t0 plus, okay? And then again, what happens is that the result of this integral is actually equal to the function computed in t0, okay? So this is a property of the direct impulse. So we get that. So if we look again at our function, so at our coefficient, so we will have Cn equal to 1 over t, the integral, okay, computed from 0. So let's write directly the result. Okay, the integral computed from 0 to t of this train of impulses. From between 0 and t, there will be only one impulse, okay? So actually, when we compute this integral, this will actually be equal to just e power minus j n omega s capital T, okay? So it will actually be equal to the function when the impulse happens, and that will happen at capital T. Now we replace capital T, and we replace omega s, so this is actually equal to 1 over capital T, e power minus j n, 2 pi over t, capital T, and this capital T and this capital T simplifies. So this is e power minus j n 2 pi, okay? But this is equal to 1, okay? So this complex number, e power j n pi, 2 pi, sorry, is 1. Then doesn't matter, you know, that there is the n here. This will be 2 pi, 4 pi, 6 pi, and so on. It will always be 1. So this will be equal to 1 over t. So going back to our slide, the coefficients will actually be equal to 1 over t. So x star of t is equal to x of t times 1 over t, this sum. So because this comes from the Laplace, from the Fourier series of this train of impulses. And we can write this as 1 over t, the sum that goes from minus infinity to plus infinity of this term here. What this means, it's explained in the next slide. So we end up with x star of t described by this expression over here. If we compute the Laplace transform of x star of t, okay, then we have to compute the Laplace transform of this guy over here. But we see that the Laplace transform of a function multiplied for an exponential, we can use again one of the theorems of the Laplace transform. And this is basically similar to the complex translation theorem that we have seen in the Z transform. And this is actually equal to the value to the Laplace transform of x of t translated by the argument of the exponential. So again, this is a property of the Laplace transform, and if you don't remember it, go back to one of your previous courses and look it up. This means that the Laplace transform x star of s of the sampled signal is, apart from the factor 1 over t that we can forget for now, is the sum of infinitely many terms where each term is obtained as the Laplace transform of x of s translated by j n omega s. So you see that actually the Laplace transform of x of star is a sum, is an infinite sum of Laplace transform of the original signal shifted in time, okay? So this s star of s is a repetition of the same Laplace transform every time shifted in time. And this actually also produces a very interesting and surprising property of this x star of s. X star of s is a periodic function, okay? Even if x of t is not periodic. So let's prove this property, okay? So we want to prove that x star of s is periodic, is a periodic function. So we have that x star of s is equal to 1 over capital T, the sum, and it goes from minus infinity to infinity, x of s plus j n omega s, okay? Then what we do is we replace s with s plus jk omega s, both here and here, okay? We do the shift in both terms of the argument. So we have x star of s plus j k omega s is equal to 1 over capital T, the sum of x of s plus j n omega s plus j k omega s. Okay? So now what we do is that we define a new variable m equal to k plus n. And here we have that x star of s plus j k omega s is equal to 1 over t, the sum that goes from minus infinity to plus infinity of x of s. And then we see that m is equal to n plus k, so we have plus j m omega s. And this we see actually from here that is by definition x star of s. So this is actually x star of s. And obviously this is true for all k, because k here does not appear and it doesn't play any role. Okay? So this is true for all values of k. And so we have seen that x star of s is equal to x star of s plus jk omega s. So it means that there is that x star of s is periodic, okay? And in particular, the period is 2 pi over omega s, okay? So x star of s is a periodic function of period 2 pi over omega s, even though x of t is not necessarily a periodic function. This will help us in a few moments to actually make a sketch of x star of s. Okay, so let's see why we want to make a sketch of x star of s, and we want to do it because of the next result that we have here. Okay, and the next result is that let's look at the frequency response of x star. Okay, to obtain that, we just replace s with j omega. So instead of computing the Laplace transform of x star of s, we compute the Fourier transform x star of j omega. So what happened is that this result is exactly equal to this result. So we said that the Laplace transform x star of s is the sum of infinitely many terms, where each term is the Laplace transform of x of s shifted of jn omega s. And the same is true for the Fourier transform x star of j omega, that is the sum of infinitely many terms in which each term is the Fourier transform x of j omega of x of t translated by jn omega s. So we can write the Fourier transform in this way. These help us to find the next theorem, to prove the next theorem, that is the Shannon theorem. So the Shannon theorem is a theorem about the ability for us to reconstruct or not the signal. So we have sampled the signal, and most of the time it's not possible to reconstruct the original signal. However, if some specific conditions are satisfied, then we may be able to reconstruct the signal. So the Shannon theorem tells us that if our signal has a bounded frequency, so there exists a maximum frequency, and let's call this maximum frequency omega x, then if we choose our sampling time such that the sampling frequency is greater than 2 times the maximum frequency, the highest frequency component of x of t, then x of t can be reconstructed from the sampled signal x star of t. So this is a condition for us to be able to reconstruct completely, without errors, the signal. So this is in some way telling us, okay, up to this point we said that we were not able to reconstruct the signal because, we don't have information between sampling times. Yes, that's true. However, if our signal is such that there exists a maximum frequency component, and we take the sampling time greater than that maximum, 2 times that maximum frequency component, then we are sure that between sampling time, nothing strange happens. The Shannon theorem, I have to say that it's a theoretical condition for what concern control systems, because in control systems it's very rare that the signal has a highest frequency component. But let's assume for now that our signal has a highest frequency component, and let's try to understand the Shannon theorem. And to understand this, we will use this expression over here. So let's demonstrate the Shannon theorem here at the board. So the basic assumption is that our function has a maximum frequency, okay? So x, here what is plotted here is the absolute value of the Fourier transform of x, okay? So this is the absolute value of the Fourier transform of x, and we see that actually this transform has a maximum frequency, because you see that the graph does not continue after omega x. So we see that all the frequency information, okay, is included, okay, in between minus omega x and omega x, where omega x is the maximum frequency. The height of this is 1 over t, to keep track of that 1 over t in the formula, so we don't have to remember that there is that 1 over t, okay? Now here I have 2 plots that I'm going to fill. In the first plot, we assume that the Shannon theorem is satisfied. So our sampling frequency is greater than 2 times the maximum frequency component here, okay? In the other plot, instead, this is not satisfied. What I'm sketching here is the absolute value of x star of j omega, and the same over here, okay? In both cases, everything is normalized in 1 over capital T, okay? So by the formula that we see at the board, we see that x star j of omega is actually equal to the sum of x of j omega translated at every time of this value, okay? So let's replace here in n, okay? Let's replace 0. If we replace 0, we obtain the first value. So in this case, we said that omega s is greater than 2 times omega x. So it means that omega s divided by 2 is greater than omega x. So it means that omega x, for instance, happen here. And here we have minus omega x. So we sketch our function, and this is basically the absolute value of x of j omega. Now, we want to put, instead of n equal to 0, n equal to 1. So if we put n equal to 1, then and n equal to minus 1, we do both, then this will be translated in minus j omega s and in plus j omega s, okay? So what we will have here is that the center of the plot will become this one and this one. Here we will have omega s minus omega x, and here we will have omega s plus omega x, and we will have this term here, and then something similar over here. Okay? And this obviously continues, so we will have another one here for higher values of n. Okay? So why this is a good case? Because then we can make a filter, okay? Let's, for instance, make a filter a low-pass filter, okay? A low-pass filter is a filter for low values that makes pass only low values of frequencies. So let's put the cutoff here, okay? And so what will happen is that using a low-pass filter on these, we are able to recover our signal and reconstruct the original signal, okay? What happened instead in this other case? In this other case, things are a bit more difficult because now we have that omega s divided by 2 is less than omega x. So omega x, for instance, happen here. So we have that this will be the function, okay? This is the first component for n equal to 0. But then we will have another one when this is omega s minus omega x, and this is omega x plus omega s, okay? And we will have something like that, and similarly, we will have something like this, okay? However, we have to remember that this is the sum of all these terms, okay? Then we will have another one here, and so on, okay? But it's the sum of these terms, just not, so we have to actually sum all of these. So I sketch the sum with another color, okay? And we see that the sum of this will be something like this. So when you sum these curves all together, you obtain this shape here. So you see that the Fourier representation of this signal is completely distorted, okay? We don't have anymore the original shape. So it doesn't matter if here we use a filter. So if we put a filter here, you see that this function is different from the original function, and we cannot reconstruct the signal. So you have to interpret the Shannon theorem as a theorem of the type, okay, if this condition is satisfied, then maybe we can reconstruct our signal, okay? If that condition is not satisfied, then for sure we cannot reconstruct the signal, okay? Now, why I said maybe we can reconstruct the signal? Okay, there are two things to consider. One thing is that in control systems, this situation in which you have a maximum frequency is very rare. The reason is that in practice, for instance, our signal will have some noise. If you have noise, noise usually appears in all values of frequencies, so it's an unbounded frequency, is unbounded in frequency, so this means that we cannot actually apply the Shannon theorem, okay? The other question is that this type of filter is ideal, and we cannot actually apply, you cannot actually build an ideal filter, and we will discuss this very briefly now. There is also another matter, the fact that Shannon theorem gives us this suggestion on the sampling time, on the sampling frequency that has to be, so the sampling frequency has to be greater than 2 times the maximum frequency. Even if that's the case, if this is a maximum frequency, what we will like in practice is that this omega s is much, much bigger than 2 times omega x. And the reason is that we will see that the sampling time is related to the stability of our system. And the smallest the sampling time, the better are the stability properties of the system. As I just said, there is the problem that the filter that then we want to use to reconstruct the signal, even when the Shannon theorem holds, it cannot be realized in practice, but only an approximation of that can be realized. This can be seen here. So let's assume that the Shannon theorem holds. So we are in the case in which there is a maximum frequency and the case in which omega s is greater than 2 times omega x. As I shown before, we want to build a box around the low frequencies. So to do so, we want to build a filter that is done in the following way. So it's a filter that is equal to capital T when the frequency is between omega s divided by 2 and minus omega s divided by 2, and 0 elsewhere. So it's the box that I shown in blue before on the board, okay? And the fact that here we put the capital T is because that will simplify with 1 over capital T and will give us the original signal, okay? The problem is that if we compute the inverse transform of this signal, what we obtain is this expression here. So if you compute the inverse Laplace transform or Fourier transform of this signal, we actually obtain this expression here. This expression is called sinc, okay? Is a function that is used obviously often in signal processing. However, in control systems, this sinc function cannot actually be realized. Because if we look at the plot of the sinc function, okay, you see that the behavior, the continuous time behavior is the following. Now there is an issue. And the issue is that in practice, you have your system, and your system is, your signal is 0 for negative values of time, okay? So the output of your system will be 0. Now, at the time t equal to 0, we provide as input to the system an impulse, okay? And the system will start to perform. The problem is that the response of the sinc, okay, to this signal will be both forward in time, but also backward in time. So the response to something that happened at time t equal to 0 somehow happen also before t equal to 0. So this is physically impossible, okay? So for this reason, in control systems, we cannot actually use this ideal filter, okay? So in signal processing, it may be possible to implement some approximation of this ideal filter. However, in real-time control conditions, we cannot use this ideal filter, and we have to rely on very coarse approximation. And the coarse approximation are actually the whole device that we are studying in this course. In this slide, again, I want to point out that if instead the Shannon theorem is not satisfied, so omega s is not greater than 2 omega x, then it's not possible to reconstruct x of t, even if we have an ideal filter that we cannot actually implement. Okay? This is because, as I shown in the graph before, with the x star of j omega, when this condition is not satisfied, then there is this problem of overlapping and the sum of the various frequency components distorting the signal, and this phenomenon is actually called aliasing. Note also that while in signal processing and communication, the signals are often band limited, so there is a maximum component, a maximum frequency component, and we can apply the Shannon theorem. In control application, usually the signals are not band limited, so the Shannon theorem cannot actually be applied. And the reason, again, as I just said, is that there is, for instance, noise. Okay? The issues caused by the reconstruction of the signal are summarized in this slide. In the first figure, we see the problem of folding. So when the Shannon theorem is not respected, what happens is that the same frequency response, when repeated, overlap with itself. And so there is a range of frequency in which there is this overlap that is called folding. The folding then causes also the fact that for what concern S star of j omega, then the actual function is distorted with respect to the original function, because where folding happens, then we're going to do the sum of these two curves, and we get this shape over here, and so on. So this causes this phenomenon that is called aliasing, and I just explained before. Then there is also another issue that I didn't cover, that is the problem that happens when the sampling frequency is chosen as a multiple of the frequencies of the signals that are in the signal that we want to sample. Let's consider, for instance, a signal x of t that is composed of the sum of two signals, x1 and x2. x1 is sine of t, and x2 is sine of 3t. So the sum of these two signals is shown here. Now, let's assume that we sample every this amount of time. So we sample this value, then this value, then this value, then this value, and so on. And here we see the sequence resulting by this sampling. Now, what happens is that if you look properly, you see that this sequence is also the sequence that is generated by sampling just this signal. In fact, it happens that the sampling time has been chosen such that it happens when this other sinusoid is always 0. So at this instant of time, this is 0. At this instant of time, this is 0, and so on. So what happens is that we have chosen a frequency that is not large enough to actually include all the high frequencies in the signal. So in particular, there is this high frequency that is not properly sampled by this by the chosen sampling time. So this is basically another way also to state the Shannon theorem, and another effect that can be caused when the Shannon theorem is not satisfied.